Okay, we're going to be looking at the ratio test now. Since the ratio test uses ratios, we of course want to make sure that the denominator is never 0. So you'll note in the ratio test that says that the series should have non-zero terms. And notice here that this is just shorthand for what you usually see with bounds saying from n equals, say, 1 or 0 to infinity of a sub n. So this is just shorthand. What the test says is that this series will converge if the limit of the ratio of the nth plus 1 term over the nth term is less than 1. So again, this is as n goes to infinity. So just remember that this notation is our like function notation when we're looking at substituting n plus 1 into our series expression. And this term down here is the nth term. So what this really is saying is that if we look at any term over its previous term, if that ratio as n goes to infinity is less than 1, so in some sense this means the terms are getting smaller, then we expect the series to converge. So hopefully that makes sense. The ratio test also says that if this limit of the ratio is greater than 1, or if, of course, equal to infinity, which is also greater than 1, so it's, you almost don't need to write this expression here, but so if this ratio is greater than 1 or infinity, then this series will diverge. Again, this should make sense because if the nth plus first term over the nth term, if this is bigger than 1, that means the terms are getting bigger. Now, the ratio test is inconclusive if this ratio equals 1. Remember, as we've said several times, there is no test that always works, so there's always some case where the test is inconclusive, and this is the scenario for the ratio test. So let's look at some examples. So let's first just note that the nth plus first term is the term we get when we plug n plus 1 in for n into our original expression. So that's the nth plus first term, and the nth term is just the original piece inside the summation. Let's set up the ratio now, and it is the ratio of the absolute value here. So we get a somewhat messy quotient with a fraction within a fraction, so let's use just a little bit of simplifying. So we take the denominator, we flip, and we multiply. Now notice we can simplify expressions here, because here we have 2 to the n plus 1. Remember, this is, let me do this in a different color. This is 2 to the n times 2 to the 1 if we're using properties of exponents. So we have a 2 to the n in the numerator and a 2 to the n in the denominator. That's one place we'll be able to simplify. And remember also n plus 1 factorial is n plus 1 times n minus 1, etc. And it's going to be n factorial here. So we're going to have a factor of n factorial in the denominator and 1 in the numerator. Okay, so we see we simplified, and I got a little color happy here. So we're left with the limit as n goes to infinity of 2 over n plus 1. So hopefully you see what that equals, and we get 0. So if we scroll back up to the test, we remember that if the limit goes to some value less than 1, which 0 is certainly less than 1, then the conclusion is that our series converges. So here we go, our series converges. Let's try another example. I'll set up the ratio, which is a big mess, but again, make sure you can follow that all the expressions in this, everything up in this part is replacing n with n plus 1, and down here we just leave n alone. So we have this very huge ratio. We're going to want to, again, simplify by flipping and multiplying. As usual, we have some things that will be canceling, so take a moment and see if you can find them all. I find that rewriting my exponents helps me see the cancelings better. And so I'm left with n plus 1 squared times 2 and 3n squared in the denominator. Please be careful when you're canceling that you really make sure you keep all of the terms that are left so you don't drop any terms. And now we look at the limit as n goes to infinity. In the numerator we have a second degree polynomial. In the denominator we have a second degree polynomial. So we know that this limit should equal the ratio of their leading coefficients. If you can't see the leading coefficient without actually foiling this expression out and distributing the 2, then you should actually go ahead and do that. But I can see that if I square n plus 1, I'm going to have n squared with a 1 as a coefficient here. When I multiply it by the 2, I'm going to have a 2n squared in the numerator and a 3n squared in the denominator, so I get 2/3 as for my limit. Again, if you can't see that, then go through the math and pause the video and make sure you can confirm that. So since 2/3 is less than 1, our ratio test tells us that our original series converges. Let's look at another example. I need to warn you that this example might take up more space than you have in your notes, so you may want to either write small or write on a separate piece of paper. let's set up the ratio. So here we go. Remember that everywhere there was an n, you're replacing with n plus 1. So we've got everywhere lots of n plus 1s. Let's simplify by flipping and multiplying. And then let's simplify anywhere we can. So notice our n factorials will cancel. And also we have an n plus 1 to the first power that'll cancel. And we're just left with n plus 1 to the n over n to the n, which I've written as the expression n plus 1 over n all to the n power. Now when we try to evaluate this limit, notice that when I substitute infinity in some sense, we get infinity over infinity to the infinity power. This is certainly of indeterminate form where we have an exponent. So hopefully you've guessed it. Yes, we're going to need to use our natural log sort of trick to get that exponent down. So first step with doing that is set our limit equal to y. And can you remember what the next step is? Hopefully you said take the natural log of both sides. And because we have a continuous function, we can switch the roles of natural log and the limit. Now if you're worried about the absolute values here, you don't need to. Since we're taking the natural log of an expression, we know this has to stay positive anyway. So the absolute values are just forcing that to be true. So we still can take this n and pull it down in front using our log property. From here, if we want to try to apply L'Hopital's rule, we have to write this product as a quotient, which we do so by writing this term as, by dividing by the reciprocal. Instead of multiplying by n, we're going to divide by 1 over n. Okay, so I've scrolled down to make more room for myself, and I've written this as a quotient. So we have the natural log of n plus 1 over n over 1 over n. Direct substitution gives us natural log of, this expression is going to 1. So this is going to 0 over 0, which is indeterminate form. So now we can apply L'Hopital's rule. So the derivative of the numerator is going to be 1 over this expression here. So that's really just the reciprocal. So we get n over n plus 1. And then it's times the derivative of this expression. So that's going to require a quotient rule. Okay, so here's our derivative of the inside. And again, here I made a comment if you didn't follow how we got 1 over n over n plus 1. So this is the derivative of our numerator. And now we need to take the derivative of the denominator. Remember that this is n to the negative 1, so the derivative is just negative n to the negative 2. Okay, I scrolled down to give myself more space. Again, I warned you. Okay, let's clean this up a little bit. In the numerator, we have n minus, when we distribute this, it's going to be a negative n and a negative 1. So it simplifies to just negative 1 over n squared, right, because the n's are going to cancel. And this denominator, negative n to negative 2, is just negative 1 over n squared. So in fact, we have a single factor in the numerator that we also have in the denominator, so those cancel. And so we're left with the limit as n goes to infinity of n over n plus 1 equals the natural log of y. This limit we can easily evaluate. Either you apply L'Hopital's rule and get 1 over 1, or just notice that these are first degree polynomial over first degree polynomial, so the quotient of the leading coefficients is just 1. So either way you look at it, this limit is 1. So we now solve for y, and we see that the limit equals e. So the ratio of the nth plus first term over the nth term, so this is RatioTest, is equal to e. So do you remember what that means? It means our series diverges, and that's since e is greater than 1. Okay, let's practice some more. What I would recommend you do is try to so pause the video and try to do these problems on your own, and then check to see if you get the same thing I do. You'll notice that I did skip a step by rewriting the ratio as a product in the first step, and when we simplify, we get just n over 3, and so the limit goes to infinity, which tells us our series diverges. Let's try another one. Okay, with this one, we can simplify a little bit. What I want to point out for you not to do is if you expand this out by foiling, which some of you may want to do, what you are not allowed to do is you cannot cancel this n squared with this n squared, since this n squared is just one term in the entire factor n squared plus 2n plus 1. And we can't cancel terms, we can only cancel factors. So do not cancel these n squareds. I see students do it all the time. So we have to leave it as is, and we get either the expression with the denominator expanded or not. Either way, it's a second degree polynomial over a second degree polynomial, so this limit equals 2, which tells us that our series diverges. Let's do some more examples. So this next one we'll notice actually is an alternating series, so you might think to yourself you should do the alternating series test, and you certainly are welcome to try. What I want to point out is something that I didn't explicitly say about the ratio test, and that is that if the ratio test tells you that the series converges, it actually converges absolutely. So what that means is if you perform the ratio test on an alternating series and you get that the limit goes to something less than 1, the series converges absolutely, and you don't need to check to see if it's absolute or conditional convergence like you do with the alternating series test. It will just automatically be convergent absolutely. So that saves you a little bit of time. If it diverges, it still diverges. So let's set up the ratio for this problem. So notice now that when I replace everything that had an n with an n plus 1, I still have this -1 to a power in both here and here. Since this whole expression is in absolute values, those terms won't matter because really this is either a positive or a negative number. You can feel free to go ahead and leave it there and simplify it, but you also could feel free to just eliminate it. It's not part of the problem anymore since it's in the absolute values. I'm going to leave it here in gray so you see that it really won't matter. And let's continue on. After simplifying, we see we get 3/2 n squared over a negative n plus 1 quantity squared. So this is a second degree polynomial over a second degree polynomial, and so the limit will equal the ratio of the leading terms, which will be -3/2. However, since we're in absolute values, it's going to be just a +3/2. Since this is greater than 1, we get that our series diverges. When you look at the next example, what do you think about this when you think about trying to do this problem? Hopefully you say that's a p-series and p is greater than 1, so it converges. And you could happily move on with life. If you wanted to see what happens if you do the ratio test, you'll actually see that you get an inconclusive result, and that's since the limit will be 1. So you don't want to make life hard for yourself. If it's a p-series or a geometric series or one of these easy ones, you want to stick with what you know will work. Let's try the next series. So yikes, this one looks kind of crazy. What I want to warn you about is be very careful when you're putting in n plus 1 into this expression. This denominator, when you replace n with n plus 1, the 3 will distribute, and this is actually 3n plus 3 factorial, not 3n plus 1 factorial, which a lot of students accidentally do. There's also lots of factorials and a big mess here, so we have to be very careful when we're simplifying. Okay, so let's look at a couple things. First of all, in the numerator we have n plus 1 times n factorial, right? That's what our n plus 1 factorial is. This quantity squared. Since it's a product, I can write this as n plus 1 squared times n factorial squared. The property I'm using of exponents there is if I have a product of a times b to the nth power, that will equal a to the n times b to the n. So that's our numerator. In the denominator, 3n plus 3 factorial, remember, is 3n plus 3 times 1 less than that, so 3n plus 2 times 1 less than that, 3n plus 1 times 1 less than that, the 3n, and then from there on in, the 3n factorial we'll leave it as 3n factorial so that we can cancel here. So now in the numerator we have our n plus 1 squared, and we have our n factorial squared, so we're going to also be able to cancel with this n factorial squared. And so when we simplify, in the numerator we have a second degree polynomial, in the denominator we have a third degree polynomial, so hopefully you realize that that means that this limit will actually just go to 0. And so our series converges by the ratio test. Again, if there's anything I did there that you don't understand, make sure you pause the video or rewind it and look at it again to make sure you get it. And the next example, again, we have p-series, and so there's no reason to apply the ratio test. In fact, if you try to apply the ratio test, you'll get an inconclusive result. So you just have to remember the p-series test tells us that the series will converge if p is greater than 1 and diverge if p is less than or equal to 1. Let's look at this last example. So set up the ratio. Again, be careful everywhere you're placing your n plus 1 that you think about what's really happening. If there's a coefficient, that coefficient is going to distribute. Also realize here that I did drop the -1 to the n power, since we already showed that once it's in absolute values it's not going to play a role in the ratio test, so we might as well drop it. Okay, let's go ahead and simplify this expression. Notice in the numerator this is a 4n plus 4, so we get 2 to the 4n times 2 to the 4. And in the denominator, when we distribute our 2, we get 2n plus 2, but plus another 3, so we have 2n plus 3 factorial. That'll be 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. And here we can now simplify, and so we're left with a constant 16 over a second degree polynomial, so this limit is going to go to 0. So our series converges, but again, since it's alternating series, we actually have to note that it converges absolutely by the ratio test.